even in a situation where the operator shut down the emergency core cooling system, we melt 60% of the core. We detonate hydrogen within the containment building. We get so much radiation that literally it's reading 800 rem inside the containment building. That system prevented any meaningful or any public health consequences to either the general public or to the operators of the plant, which in my mind is why one of the reasons why 3 Mile Island is one of the greatest arguments you have for nuclear safety.
Welcome back to Decouple. Today I'm pleased to be rejoined by returning guest James Krellenstein. And we have a very special episode building off of the news of Constellation and Microsoft signing a long-term PPA for the restart of Unit 1 at 3 Mile Island. We thought, why don't we talk a little bit about that other unit there, Unit 2. James, I've heard you refer to this in the past as I don't want to misquote you, a really cool accident. I'm really looking forward to a chat here and discussing what happened and really understanding the aftermath and implications. So without further ado, James, welcome back.
Thank you so much, Chris, for having me. I think, 3 Mile Island, in so many ways, for better and definitely for worse, marks a sort of beginning and an end of an era, especially in U.S. nuclear, but maybe in Western, sort of non-Russian, non-Chinese nuclear as well. It really fundamentally transformed the way that nuclear power plants are regulated, are constructed, and are operated in the United States. And although I think we talk a lot about the downside of what happened at TMI, I mean, let's just be frank, right? TMI, although as we'll see, a very severe accident in terms of what happened, no one was harmed. The amount of radiation that was released was less than what a nuclear power plant is allowed to expose the public to just through regular operations every year as part of NRC codes, and really demonstrated, I think, was a vindication in many ways of the defense in depth safety philosophy that does exist in the U.S. nuclear industry. On the flip side, it really did transform the way that we regulated, constructed, and thought about nuclear safety, primarily because this sort of accident sequence, as we'll talk about, was never supposed to happen and was not particularly the root cause of it, which I think is arguably with human-machine interface and the way that training happened, was not something that prior to this, the nuclear industry had spent that much time really evaluating. So I think, one of the things that on the upside, although this is, and it's true, really drove up the cost of construction of some nuclear power plants that were under construction when TMI happened. The flip side about this is that the regulatory changes coupled with the change of the industry culture allowed us to really get nuclear power plants to be highly, highly reliable sources of baseload generation. We don't talk about it that much, but prior to 3 Mile Island, nuclear power plants in the United States were operating at about 55% capacity factor. So around what an offshore wind a good offshore wind a turbine would generate at. And the industry response, coupled with the creation of new organizations like the Institute of Nuclear Power Operations, coupled with some regulatory changes and research that was sort of started by the NRC and the Department of Energy, really allowed us to begin this really rapid climb right after the accident. It almost looks like a cliff in terms of capacity factors to get where we are today at 90 or 91 or 92% or 93% capacity factor fleet-wide. And what's so interesting about this is that every single plant that is driving that, with the exception of Vogtle 3 and 4, was started construction before 3 Mile Island happened in April of 1979. But I don't think we talk a lot about what actually happened at the accident and why that's kind of a really good way to think about nuclear power plants, about how pressurized water reactors work, and also to really think dynamically from an engineering perspective of how all these systems integrate together and how the humans who are actually operating the power plant think about the operations and make choices during the operation of an abnormal operational occurrence. So I think that's a really good way to start, is to sort of dive in to what actually happened at TMI.
Yeah, I'm looking forward to how you're going to break it all down. I watched I think Sci-File has a great YouTube video. Of course, Jesse Freeston of Decouple Studios made a reaction video to 3 Mile Island Meltdown, a Netflix special. But yeah, I mean, you can take it into a lot of detail, engineering detail. ChatGPT finally really brought it into focus for me and clarified it. But I'm looking forward to hearing the Krellenstein explanation. So
yeah, so I'm actually going to use untraditionally visual aids here, I think, to think about what happened at TMI. And I only have a couple of graphics, but I think the most important thing to start is a basic schematic or a representation graphically of what the 3 Mile Island pressurized water reactor looks like and how it works. So 3 Mile Island is a Babcock's and Wilcox pressurized water reactor. And this is actually the rarest type of PWR in the US fleet. And it has 2 steam generators, and it has a unique type of steam generator called a once-through steam generator, which we'll talk about in a second. But just to get ourselves a little bit acclimated, the way a PWR, whether it's Babcock's and Wilcox or Westinghouse or Framatome, works is that you have 2 different sets of water, right? You have one set of water, which is what's called the reactor coolant system, right? That is under a very, very high pressure. So much high pressure that even though we're at hundreds of degrees Celsius, right around 320 degrees Celsius, that water never boils. And the way that we make steam, which of course is necessary to turn the turbine to make power, is we run that water through a heat exchanger called a steam generator. And what that steam generator consists of is thousands of tubes that sit in a bath of less pressurized water, which we call the secondary water. So what happens is the water goes through the reactor core, heats up, is still liquid. That liquid water goes through the top of the steam generator in the case of a Babcock's and Wilcox plant and goes all the way down. This is why it's called a once-through steam generator. It just goes one time through. It doesn't have that U-bend that the other steam generators in pressurized water reactors have. And in those pipes that have that reactor coolant are sitting in this bath of what we call feed water. And that feed water is at a lower pressure. That heat transfers through the walls of the steam generator tubes and boils that feed water, making steam. And once again, these water never mix, right? That primary water or reactor coolant water never touches, ideally, that secondary water that actually turns into steam. So that steam then goes into the turbine, expands in the turbine, which spins the turbine, goes to the generator, turns the transformer, and that steam gets condensed by water. And then that water, that condensate that comes out of the condenser, gets pumped back to the steam generator to be boiled again, to be turned into steam. On the reactor coolant side, that water is dropping temperature as it boils water, and that cooler liquid reactor coolant gets spun by the reactor coolant pump, gets pumped through again the reactor core, gets heated up again, and goes to the top of the steam generator to make that boil that water. So that's a nice little circuit that we have going here, right? And what the key thing to understand is that we have to keep the reactor coolant moving, right, by the reactor coolant pump. And critically, we got to keep water moving into the steam generator through that feed water pump, right? Because if you cut off that feed water, that steam generator level is going to drop and eventually dry out. So that's really where we sort of start on the basics of where a PWR are. And I want to flag one component of this system that is going to be really, really important for what happened at 3 Mile Island. And it's this device called a pressurizer. And what a pressurizer is remember how I told that this thing is at ideally 2,195 pounds per square inch. Right. What the pressurizer is a system, is a big tank. At the bottom of the tank, and this is what it looks like at 3 Mile Island, at the bottom of the tank, it has heaters, right? And there's a big steam bubble at the top of that. That's the only place, ideally, in that system where we have steam on the primary system. And this steam bubble acts as like a piston. Basically, water is incompressible, which means that when we change the volume of water, you can have dramatic increases in the pressure of the system. What this steam bubble does is it allows us to basically control the pressure of the reactor coolant system. And how do we do that? If we want to increase the pressure, we basically make the steam bubble bigger. If we want to decrease the pressure, we put these sprays on and literally condense that and make that bubble smaller. And when there's any sort of change in reactor coolant pressure, this bubble acts as a shock absorber. It basically makes sure that the reactor coolant system doesn't go through wild perturbations or wild sort of swings in pressure, which would happen if the system was so-called solid with none of the steam bubble. And there's a really important reason that I'm talking about that will come very apparent. The operators in a Babcock's and Wilcox PWR especially are trained to never let the steam bubble go away. They always want to maintain that steam bubble there. And if they, which is preventing the system from going what's called solid, which means that there's no steam bubble. So does that make sense sort of from the basics of how this thing works?
Yeah, I think we're all pretty oriented now.
Okay, great. So what happens at 3 Mile Island? So it's 4 a.m. Literally, it's 4 o'clock, 00 and 38 seconds on the clock. So what's the first thing that happens? So operators are doing some work on a high-pressure air system that is used to control the valves in the plant. And as a result of that, this valve right here, that's in between the condensate pump and the feed water pump, accidentally is closed, slamming shut the source of water that the condensate pump needs for the feed water pump. That means that the feed water pump shuts down. And when the feed water pump shuts down, the turbine shuts down. So all of a sudden, that turbine, which is absorbing a huge amount of the heat that's actually being converted into electricity that the reactor coolant system is providing, right, suddenly goes away. So the reactor coolant system starts heating up. And not only does that turbine trip, but there's no more feed water being fed into the steam generators that replaces the water that is being boiled and turned into steam. So all of a sudden, the steam generator level starts dropping, and the temperature of the reactor coolant system starts getting higher and higher. And as a result of that increased pressure and increased temperature, the pressure in the system goes up and up and up. So within the first 2 seconds, to give you an idea of how quickly this thing works, right, for the first literally 2 seconds after that condensate pump shuts down and the feed water pump shuts down, this valve on the top of the pressurizer is signaled to open by the plant's automatic logic controls. Right? It basically says the pressure is too high and we need to basically let off some of that pressure and basically open what's called a pilot operated relief valve, which is right up here, and let some of that steam off to lower the pressure.
What would happen if it didn't open or if you didn't release the pressure?
So that's a great question. So actually on this, there is the pressure operated relief valves. Then there are what are called the safety relief valves, which are SRVs, which are spring loaded valves, or the safeties, you'll hear them called, the SRVs. And they basically just open literally when the mechanical force of the reactor coolant system gets larger than the pressure, than the force of the springs holding them down. And the reason why we don't generally like to have those operate is because the safeties often, when you lower the pressure, they don't seat properly, right? So, you don't generally want to have the safeties, relieve in any situation. But even if they did, it's a really bad situation because you'll have to generally send someone into containment to reseat those safety valves if they get open. But the idea here is that the system is designed with multiple different redundancies to prevent an overpressurization transient that could actually pressurize components of the reactor coolant system so they burst. We don't want to ever burst them, so we have multiple redundant systems that prevent that overpressurization. The idea here is that this is a sort of a system that the electronic analog logic opened up because the RCS pressure was too high. So you can see those relief valves are redundant systems over here, and they just vent directly, I believe, into containment. So what happens is at 2 seconds, that valve opens up. But that valve, or what we call an electrohydromatic relief valve or pilot-operated relief valve, is relieving pressure, but the reactor is still on. The reactor hasn't scrammed yet. In the original pre-3 Mile Island configuration, the accident, the reactor did not automatically shut down on a turbine or feed water pump trip. So what's going on here is that pressure, that pilot operated relief valve, which is relieving some pressure from the system, is not doing it well enough. So we reach the scram set point at 8 seconds. In 8 seconds into the accident, the reactor automatically shuts itself down by inserting all those control rods into the core. And right now, this is a totally normal response to a transient. Feed water transients, turbine trips, and so on are things that are called in nuclear engineering anticipated operational occurrences, or AOOs, which is a really complicated way of saying that these are things that we expect during the plant life to happen, and the plant should be really well designed to be able to deal with that situation. And so right now, although this is obviously an abnormal situation, it's not anything remarkable. Turbines trip, feed water pumps shut down. This is something that the system is designed to be able to do and not even be considered a major accident. So there's nothing here right now that's really that abnormal. But what happens is a couple seconds later, the reactor coolant system pressure starts dropping because the reactor is shut down, so we're no longer emitting that heat. The reactor coolant starts cooling down and shrinking, which is actually reducing the pressure even more. So the logic in the system basically says that pilot-operated relief valve should shut down, should close. And that's a solenoid-activated valve. And the logic works perfectly well. That PORV shuts down perfectly, and it's de-energized. The problem is there's literally a mechanical fault in that valve. That valve gets jammed open due to an error, essentially a fault actually in the design of this valve. And the critical thing to understand, and this is the beginning where we start departing from a regular sort of anticipated occurrence into an accident, is that the light in the control room that indicates what the position of this valve is does not indicate the actual position, but rather whether that solenoid is energized or not. The solenoid is de-energized, so the light goes out in the containment, but that valve is stuck open. So we're only seconds in to this transient. So I want to pause there.
Just quickly, and it's not even important, but what does solenoid mean?
Oh, a solenoid is basically it's a coil of wire that basically creates a magnetic field, and then that can actually literally make a piece of metal move through it. When that magnetic field's on, gets stuck open, or when the solenoid's de-energized, it can fall through, right? So it's like a little electromagnet that literally moves something up or down.
So, I mean, so far, this is great. It's a lot of detail, but not too much. But yeah, what's shocking again is just the rapidity under which this is all happening. And we're going to get into, I think, this being a real human factors element. But so far, this is just kind of the logic of the plant responding, and you kind of need that logic there to do it, because a human being just can't respond quickly enough to.
Right. I mean, I think what people don't understand is that in a large pressurized water reactor, because we're not boiling any of the water there, and we're making just so much heat in the reactor core. The reactor core is literally one of the densest energy places that, in almost anywhere in, I don't want to say the galaxy, but it's in the solar system in some ways. It's shocking to realize that the core of a pressurized water reactor, right, has about a power density that's about 300,000 times higher than the center of the sun. And in order to keep this thing running and cool and stable, right, when the reactor's at full power, these reactor coolant pumps are moving 15 tons of water per second through the core. And what's amazing is that we have gotten these machines to do that amazing amount of work so reliably that often we can go without ever stopping at 24/7, 365 days a year. That pump never trips, and it's just continuously moving that massive amount of water through the core every second. But it also means that when we have an abnormal situation, if we don't shut down that reactor, things can evolve very, very quickly, which is why there is, as you noted, a quadruply redundant system called the Reactor Protection System, or RPS, that is constantly monitoring a huge number of parameters to see if anything, gets out of whack. And if that sort of is detected, it can shut down that nuclear fission reaction in about 2 seconds. So it really is an extraordinarily powerful system that has amazing safety features that are designed to keep the system safe and stable, and it works. So now we're 8 seconds into this accident. The control rods have fully inserted into the core, and that nuclear fission reaction is no longer happening. In other words, the reactor is what we call subcritical. But that's not the end of the story, because any nuclear reactor, when you shut it down, even though the fission power goes to zero, that is the effective amount of power that's being generated by prompt fission reactions or delayed fission reactions, what we still do have is what we call decay heat load. So what's going on is that there are radioisotopes that have been generated as part of the nuclear fission reaction in the reactor core that are still generating a large amount of heat. So we drop from around, in this case, a reactor that's a small, slightly less than 3,000 megawatts thermal, right, down to about 6% of that power. So we go from 100% of that 3,000 megawatts thermal, right, to approximately slightly less than 300 megawatts thermal, right, to about 6% of that. Actually, in reality, around 200 megawatts thermal. And that is not from fission anymore. That is what we come from decay heat. And that's why we still need to cool the reactor core, right, even when the reactor is scrammed or shut down, because that heat is alone enough to melt those fuel rods, and why it's really essential that we keep this system being able to keep that core covered and cooled.
Yeah. I mean, is there any other phenomenon like that in terms of an object that produces decay heat that human beings handle? Like I'm thinking, I don't know, like a big piece of molten steel or something. And I'm just trying to get a sense of what like 200 megawatts thermal means in terms of.
Well, so I guess the difference with like a molten steel is that's what we call latent heat, or just the heat, the heat of it being at a certain temperature. This is not the same thing. It's not like it's the fuel is really hot and we got to cool it down. It's that the fuel is literally just generating heat. It is generating power that is new, that is just coming from the various decay reactions that are occurring in the reactor core. And this is what every meltdown, I mean, I don't really consider Chernobyl a meltdown, although a meltdown did happen at that. But like, if you think about Fukushima Daiichi, the reactor was scrammed. It was shut down. So was 3 Mile Island. The reactor was in a scrammed configuration and that's where we actually started damaging and melting the fuel. And let me just be clear, even with the reactor fully shut down, if we don't keep, the core covered, the core will melt and will melt fully. But we have a problem now, right? And that problem is that this valve is open, it's stuck open, leaking reactor coolant. And what this is called is, if anyone knows nuclear engineering, this is a classical loss of coolant accident, or LOCA. And this is what we call a small break LOCA. It's a small amount of fluid that is leaking out, but continuously leaking out. And it's not enough to rapidly depressurize the reactor coolant system, although reactor coolant is, the pressure is dropping. There's another incident that occurs here as well. Remember how I told you that this main feed water system shut down and was no longer getting new feed water into the steam generator? We have in the system a whole nother set of triply redundant sort of systems in a plant like 3 Mile Island called the auxiliary feed water system, which is right down here. And that system is designed for exactly this sort of incident that just occurred. When we lose the main feed water, the auxiliary feed water system automatically starts. And the idea here is that this continuously pumps water into the steam generator, such that even with this reactor coolant pump shut down, natural circulation through the reactor coolant system is enough to take away all of that decay heat and keep the reactor coolant system, the reactor core covered, and the reactor coolant slowly cooling down, right? The RCS slowly cooling down. So that auxiliary feed water pump, as designed, automatically spun up right as that main feed water system shut down. But here's the problem. There were a block valve here that had been shut a couple days earlier for maintenance activities. And even though it was against plant procedure, those block valves remained shut. And it turns out that in the control room, even though there were lights that were indicated that these block valves were closed, those indicator lights were literally covered by tags, like paper tags, that were indicating that a certain system was under maintenance. So the operators, when glancing at this, couldn't easily detect that those block valves were shut. So all of a sudden, we have a situation where we have a stuck pilot-operated relief valve leaking reactor coolant from the reactor coolant system, and we have no feed water going into the steam generator. So the level in the steam generator starts dropping, and eventually the steam generators completely dry out. So we are now at the point where we've gone from a normal sort of response to something that is assumed to occur to the system not responding as it was designed, right? We have a stuck valve and we have no feed water going in to the steam generators, and the steam generators drying out.
And that auxiliary feed water pump, is that the same thing as the emergency core cooling system?
No, it is not. So the emergency core cooling system, which we're about to get to, is not the auxiliary feed water system. The emergency core cooling system, which consists of two trains of high pressure injection, or HPI. In this case, sometimes it's called HIPC or HPSI, high pressure safety injection, and LIPC, which is low pressure safety injection, directly inject water into the reactor coolant system. So into that primary system. The auxiliary feed water system is directing water into the secondary system on the other side of the steam generators. Right? So they are two very distinct systems, and we're about to get into where that distinction becomes critical. So let's just pull back now. We have stuck valve. The auxiliary feed water pumps are running and spinning, but the water is all literally being blocked by this block valve that is closed. The steam generators have dried out, but luckily what's going on right now is the excess heat being generated is literally actually being transferred. The reactor coolant's boiling in the pressurizer, and that steam is leaking into a drain tank in the containment building that's rapidly filling up. And what this stuck valve means is that the reactor coolant system pressure is dropping, as to be expected. It's like a pressure cooker. When you open that valve up on your pressure cooker, the steam goes out and the pressure inside the pressure cooker is dropping and dropping and dropping. And this is where that emergency core cooling system comes into play. The emergency core cooling system, like all their emergency systems in a nuclear power plant, are controlled by a system called the emergency engineered safety feature actuation system. And what that is also doing is monitoring a bunch of parameters, even as the reactor shut down, to see if we have a leak or a LOCA situation. And because that pressure in the reactor coolant system is rapidly dropping, the emergency core cooling system automatically turns on and begins flooding and basically injecting water back into the reactor coolant system, more than making up for the amount of water that's leaking out of that stuck valve. And had the accident just stopped there, even if the operators, which they eventually did a couple of minutes later, realized that block valve was closed and there was no feed water happening, even if they never were able to basically detect that this safety valve was open, that HIPC actuation that happened automatically would have prevented anything. This would have been still an incident, but the core would have been never uncovered. There never would have been a meltdown at 3 Mile Island. And in fact, even if one of the emergency core cooling systems was broken or didn't respond, the other backup emergency core cooling system was more than sufficient to basically maintain inventory in the RCS, even with this valve being stuck open. So right now, we're now into a definitely abnormal situation. Inside the control room, alarms start going off, indicating that the plant safety systems are saying, hey, there's likely a leak in the reactor coolant system. The pressure is way too low, and I automatically am injecting more water into the reactor coolant system to maintain level.
And how far in are we at this point?
We're in let's see, actually, I can go exactly here. So we are in about, I would say about 15 minutes in at this point, right? So at this point, we're only about 50, or even actually a little bit less than that. We're probably a couple minutes, we're 2 minutes in. I'm sorry, 2 minutes, 30 seconds in, right? We're 2 minutes, 30 seconds into where the high pressure injection begins injecting into the reactor coolant.
So far, everything's basically on autopilot right now. There's not been any real human actions.
I mean, so they're definitely the control room at this point is being very very crazy. There's a huge number of alarms going off, way more than the operators had ever seen before, because the system is having multiple different faults happen simultaneously. And that is, this valve is stuck open, but there's no direct indication that valve is open. The auxiliary feed water system is blocked. The reactor coolant system pressure is dropping. And so there's a huge number of alarms, and we're in just a regular scram situation where there's hundreds of alarms that just happen naturally, but nothing at this point. The plant's automatic safety system actuation have more than compensated for both the feed water pump trip, the stuck valve, and the auxiliary feed water pump trip that occurred. So even the auxiliary feed water block valves being closed. So even though we're in like triple or quadruple failure, depending on how you think about this sort of situation, the plant's automatic safety systems are still more than able to keep the plant in a safe configuration and have activated automatically to do so.
That's some extraordinary engineering and design, I gotta say.
Right. Now, here's where where the accident really takes the turn to the worst. Okay. So the first thing that the operators recognize about 8 minutes in is that these block valves are closed. And that is a very, very sort of disturbing revelation, to recognize that the reactor coolant system itself that the steam generators boiled dry, that the aux feed water pump that they thought had been running, and they had been running, basically had turned on, but were blocked by a valve. And one of the operators recorded that he almost ripped open the sort of the switch on the control panel to open that block valve to let the water go back into the steam generator. Now, that occurs, and that distracts the operators from having situational awareness of what's actually going on. Even though that auxiliary feed water being closed by those block valves is a very serious situation, it is in fact not the most serious situation that the reactor is in right now, which is this stuck valve that is constantly leaking reactor coolant into the containment building. And even more than that, the safety injection systems, the emergency core cooling systems, have spun up that further disorient the operators. They have a failure of the auxiliary feed water system. For some reason, the emergency core cooling system is turning on. They're starting to get alarms that this drain tank is filling up and that radiation levels are risingly increasing in the containment building, all a couple of minutes into this accident. And then something else starts happening that is very, very strange, which is that and this is actually from the actual plant, right? Although the reactor coolant system pressure, which is this line over here, dropped a lot, the level in the pressurizer is surging. So the water level in that pressurizer, and the pressurizer is at the highest point in the reactor coolant system, is the main way that they measure the level of water in the reactor coolant system. So what does this mean? They don't have a way to directly measure the amount of water that's, say, in the reactor pressure vessel, because that's always assumed to be full of water. So what they do instead, the operators look to this pressurizer level to figure out how much water is in the system. And that makes a lot of sense. That pressurizer is at the top of the reactor coolant system. So like any other system, if the water in the system is dropping, that water level should drop with it. So they use this pressurizer level as a way of a surrogate measure of how full or how empty the reactor coolant system is. But here's the problem. Remember how I said that pilot operated relief valve, which is on the top of the pressurizer, is stuck open? And that means that there's a low pressure point at the top of the pressurizer. that means that the water in the pressurizer is boiling, and is boiling really, really rapidly and violently and making steam. And like if you've ever boiled a pot of water on the stove, you notice when the water is not boiling, it's at a pretty low level. But once you've got those big steam bubbles that are coming off the bottom of the pan, the water level rises in the pot. And the same thing is happening in the pressurizer. Even though we're actually losing inventory in the reactor coolant system, the pressurizer level, which is the way the operators are trained to look at how if the system is overfilled or underfilled, is registering on the meters very, very high. In fact, way higher than they would normally have during normal operations. So like tens of inches higher, like feet higher than is normally expected. And remember how I said one of the things that they are trained to do is never let go of that steam bubble on the top of the pressurizer. That's called going the system solid, letting the system solid. So like anyone else, they say, the level is really, really high, and I have I have two emergency core cooling system pumps dumping hundreds of gallons per minute of new fresh water into the reactor coolant system. So what do? They shut down the emergency core cooling system, thinking that there's too much water in the reactor coolant system rather than too little. And this is where we really begin the pathway towards a meltdown. So I just want to pause there. At this point, everything that has happened in the system response, even though we had a feed water pump, trip, a condensate pump trip, even though the block valves of the auxiliary feed water system that automatically spout were shut, even though we had this stuck valve open, the plant had automatically responded at this point in a way that would keep it into a safe configuration. And as you noted, this is immense engineering. These safety systems and these automatic actuation systems are kind of designed brilliantly that even in this sort of, and none of these are computerized, right? These are all analog systems using relays and bistables to actuate, had brought the system into a safe configuration. If you talk to some of the Babcock and Wilcox engineers who have thought about this, is that they will say, we thought of every sort of externality, every sort of transient. In fact, there's even other things that the plant did automatically to prepare for an accident that didn't actually, weren't necessary. Like, for example, when the emergency core cooling system spun up, the emergency diesel generators automatically kicked in saying, hey, the plant's in an abnormal configuration. Maybe there's a storm or an earthquake. Let's get our emergency diesels automatically turned on to prepare for a loss of power, which never happened here. But it just gives you an idea of the level of engineering rigor that went into designing and engineering these safety systems to automatically put the plant into a stable configuration. The one thing they hadn't anticipated was that the operators would shut down that emergency core cooling system.
Enter the human factors.
Enter the human factors. So let's go back to imagine yourself in the control room of this power plant. It's 4:15 in the morning, right? You have just had a reactor scram, a feed water pump trip, a condensate pump trip, a situation where the auxiliary feed water pumps are supposed to spin up. They did spin up, but unbeknownst to you, for minutes, you let the steam generators boil dry. You have a situation where the reactor coolant system pressure is dropping, and it's dropping fast enough that the automatic safety systems think there's a loss of coolant accident going on. Simultaneously, the level in the pressurizer is really, really high, which seems totally contradictory. A situation they had never trained for. And the number of alarms at this point have so overwhelmed the one plant computer, or really two plant computers that exist, that the computer at this point is running 30 to 45 minutes behind because it just cannot keep up with printing out all of the alarms that are occurring simultaneously in the plant. And then furthermore, a couple minutes later, this burst valve on the drain tank burst open, and water starts piling up in the bottom of the containment building that gets pumped into an auxiliary building and begins signaling radiation alarms throughout the plant. that there's essentially water that's going outside of the containment causing radiation alarms. So you have a just avalanche of information being presented to the control room operators in a situation that not only had they never trained for, literally the simulator. Now, at this point, before 3 Mile Island, not every plant had a simulator, but Babcock and Wilcox, the designer of this reactor, this nuclear steam supply system, had a simulator at their headquarters in Lynchburg, Virginia, which the operators had trained upon for a couple of weeks. It was literally not capable of simulating this situation. And that situation is a situation where reactor coolant pressure is dropping and pressurizer level is surging, which leads the plant operators to make the fatal mistake of shutting down the emergency core cooling system. But to their credit, that was what they were trained to do. They were trained to use the pressurizer level as a surrogate for the amount of water in the reactor coolant system, and furthermore, to never let that steam bubble go away. And so they thought they were overfilling the reactor coolant system. Okay, so here we are. Now we are in a loss of coolant accident, a small break loss of coolant accident, and we have no amount of injection going into the reactor coolant system. In fact, the operators have at this point turned on the letdown system, pumping even more water out of the reactor coolant system than the break in the pressurizer valve allows. And the reactor coolant pumps, which are still spinning and maintaining maintaining flow across the core, all of a sudden start vibrating violently. Because what's occurring here is now the reactor coolant system, which is always supposed to be solid liquid water, except for the pressurizer, is now depressurizing so rapidly that there's boiling going on in the RCS, which is causing these massive bubbles of steam to accumulate in these massive pumps that are the size of 18-wheeler trucks, all of a sudden, which are spinning with 9 megawatts of power each, literally start vibrating violently as, rather than liquid water going through the impellers, bubbles of steam start vibrating that impeller and threaten to tear the sort of RCS apart. So the operators automatically shut down the reactor coolant pumps, hopefully relying on natural circulation to keep water moving through the reactor coolant system. The problem is that it will take 2 hours and 30 minutes before the operators recognize that this valve is stuck open. Now, there is, in fact, a block valve that is right downstream from that pilot-operated relief valve, that if they just simply close that stuck valve will be blocked completely. But because they do not recognize that valve is open, because the light in the control room is indicating that it is closed, they don't actuate that for hours. And as a result, the reactor coolant system gets totally loses a huge amount of inventory, and the reactor core becomes uncovered and begins a meltdown. Now, what occurs eventually is, and we're about 2 hours and 30 minutes into this, is we actually have melted around 60% of the core, have generated a massive amount of hydrogen. As so much hydrogen that a couple hours later, there will be a massive detonation of hydrogen actually in the containment building, which the containment building will take, and actually no one will notice until a couple days later, but it pressurizes the entire system. We melt down about 60% of the core, and it turns out that once the operators recognize that they can shut those block valves, restart the high pressure injection into the reactor core, they can terminate the meltdown sequence and prevent even more severe accident from occurring.
That was one of my questions, I guess. Like, how could it have gone worse? And I guess if they didn't turn on the emergency core cooling system and block that pilot operated relief valve, Then you could have a full meltdown, and then you'd have like corium that would melt through the reactor pressure vessel and go all the way to
Well,
China,
we
right?
had corium that actually, believe it or not, I mean, we can show some pictures of this. We have some corium that actually literally collects at the bottom of the RPV. And literally the RPV gets sort of melted away a little bit, but it never actually breaches the RPV, right? So we melt 60% of the core, but we terminate it in time to prevent a full core meltdown that actually breaches the RPV. And furthermore, actually, ironically, the operators at various times, even as they're recovering from the accident, recognizing what's going on in this situation, actually open that pressure relief valve a couple of times in order to actually have an alternative way of cooling the reactor coolant system. Basically by feeding and bleeding, it's called, basically by essentially letting off steam out of the reactor coolant system. They can take away heat and they can compensate for that lost cooling water through the high pressure injection system. Which is because they can't actually run until the system is refilled up. They can't run these reactor coolant pumps because there's way too much steam and water in the system.
So when we talk about the human factors element here, like I've got reference points in medicine, in aviation, the Tenerife accident, famously, I think over 500 people killed when two jumbo jets collided with each other during takeoff. A lot of that had to do with hierarchical communication, the captain overriding the co-pilot and the flight engineer being impatient. This sounds like a bit of a different situation in terms of just being completely overwhelmed with, I think, over 100 systems or 100 alarms happening in the control
much more
room.
than hundreds of alarms.
Like I was
100 alarms in the first 45 seconds, right?
Yeah, I was actually touring the Bruce nuclear station. We went to the control room, and it was actually with a bunch of labor and some of the kind of representatives of the left wing parties here in Canada. And they thought it'd be a great idea to simulate not an accident, but I think actually was a LOCA and their response to it. And I mean, I think a lot of things have been updated since TMI, but it was still, for me as an advocate, kind of terrifying. Like the little red phones were ringing, sheets of paper were flying off of the printer, accumulating on the floor. There were lots of lights going. Of course, the operators are cool as cucumber, and the system basically dealt with it with minimal intervention. But it was pretty amazing just to kind of go to the theater and watch something pretty wild go down.
As you say, actually the operators, this wasn't a hierarchical situation where, there were 3 people in the control room initially. And by, 40 minutes in, there were 45 people in the control room, trying to figure out what was going on in this situation. I think there's a couple of things that are happening. The first is it's what we call, the non-PC version of this is man-machine interface. Now it's called human-machine interface, which is something that actually the nuclear industry after TMI led a lot of actual innovation that didn't just translate to the nuclear industry, but also to aviation and to medicine, which is how does a very complicated system like a control room of a nuclear power plant, how does it prioritize and present data to the operators that are operating that system? And the first most obvious sort of failure here was that light bulb in the that represented whether that relief valve was shut. And it's really, really easy in an alarm situation, even if they were trained, to know that light didn't actually recognize the state of the valve, whether it was open or closed, but rather what the valve had been commanded to do. If you're doing 100 things, trying to respond to 100 different alarms, and the operators even said this, they checked, they looked at the light on the control panel, and that valve was shut. Even though that's not what the light was actually telling them. It was telling them that it had been commanded to shut. And there was actually a way and a procedure, believe it or not, to look at whether or not that valve was actually shut, which is to look at the temperature of this line, that of the pipe that basically comes off of that valve. That temperature gauge was literally behind the main control room panel, and had a other situation that often that temperature was very, very high regularly, because that valve would sometimes leak, and that leak was allowed to happen because they thought it wasn't a big safety issue. And they also didn't recognize that. They said, oh, the valve lifted and it closed, so that pipe is going to be open. So you can imagine the confusion of the operators. The operators can't obviously go into containment, go up to the pressurizer doghouse and look at the valve. So they're looking at these surrogate indicators, and all the surrogate indicators are telling them it's shut. And then they have to make the mental leap sort of to not trust their instruments and to recognize that in fact that valve is open. That's a pretty big leap of logic to be making when all these other alarms and all these other abnormal situations are happening in the plant. And just to give you an idea of one of the things that was happening that distracted the operators for like minutes in this accident is as the reactor water level was dropping and dropping and dropping, even as the pressurizer level was still high and high, and actually uncovered the core. One of the things that happened is the neutron sort of detectors in the core started recognizing that the neutron flux was increasing. And this led the operators to believe that they may have actually brought the reactor critical again. And that wasn't actually at all what was happening. What was happening instead is that water, light water, as you know from your CANDUs, shields neutrons, absorbs neutrons. And as the core became uncovered and the fuel was uncovered, the neutron flux increased, which was detected in the detectors in the control room. And they thought they were returning to criticality because they thought the reactor core was covered because the pressurizer level was high, even as the entire the reactor core was melting, and they totally misdiagnosed the situation. And when they actually thought that the reactor coolant system, that actually the core was becoming uncovered, they asked their plant computer what the temperature of the fuel was, and rather than actually printing out anything, it just printed out question marks over and over again, because the system had only been designed to basically operate when the fuel was at 700 degrees Fahrenheit and below. And when it was above 700 degrees Fahrenheit, the computer system assumed that the thermocouples were malfunctioning. So rather than actually printing out what the temperature was, it just printed out a series of question marks, which I can show you. And so literally you had to have operators go down to the cable spreading room and take a voltmeter and manually measure what those thermocouples were actually registering, because the computer couldn't actually display that information. So we have a couple of major issues that are going on in the way in which the human operators are interacting with a huge amount of data that's being presented to the operators. One is that light doesn't actually show the valve open or close. It shows what the safety systems commanded it to do. We have no direct way of measuring the actual level of reactor coolant in the system. We're just measuring pressurizer level. And three, other indicators that are safety critical often malfunctioned in the way when they are actually displaying information that was way out of the normal expected sort of response of the plant system. All of this coupled with the training of the operators to never let the system go solid, and with training on a simulator that literally could never actually replicate this exact sort of situation, led the operators to make an error that in hindsight is easy to see, but looking at it from that point is entirely understandable.
Something that seemed a bit unforgivable to me in doing some background research was that this pressure release valve had malfunctioned 11 times previously. I'm not sure if that was just in Babcock-Wilcox reactors or more broadly. They had an incident at the Davis BESS, very similar. I guess
1978 or 7, yeah.
A memo was sent out that if the reactor had been at full power, this could have resulted in a meltdown. And I guess that's a big change that happens after TMI, as the industry says, okay, we've got to. We can't be Soviet here. We have to share information because an injury to one is an injury to all. And it's just incredible the kind of speed with which, this reactor has a partial melt and writes off, I don't know how many billions of dollars it cost to construct that plant, but not consequential.
I mean, and we now know the value of that asset, right? I mean,
yes.
3 Mile Island unit number 2. I mean, maybe it would be the deal with Microsoft would be double the size of what it is today,
exactly.
Right? I think that's exactly right. I think the regulatory culture and safety culture of the industry was two things. The first was, as you noted, that electromatic the pilot operated relief valve that we're talking about, the PORV, had failed multiple times. It was manufactured by a company called Dresser Industries. There wasn't at that time a way for the operators to communicate a sort of scenario like that amongst each other. Right. The NRC steps in and really ensures that not only after 3 Mile Island, that any sort of accident scenario, not only is it communicated to all licensees, but also that the components and serial numbers and manufacturers of the components that are that occur are distributed, as well as a much larger safety culture. Right. It's not a very good safety culture to have a valve that has a known design flaw that allows it to get stuck open on the reactor coolant system happen multiple times and never address it, never fix it either. And as you noted in the Davis-Bess accident, the operators were able to figure out it fast enough that they were actually, didn't get the system into such a dangerous transient as configuration. But that is not what happened with the 3 Mile Island operators. Now, what's incredibly important to recognize here is that inside the containment building at this point, once the core melt has occurred, the radiation level inside that containment building is extraordinarily high. The detector of radiation on the top of the dome of the containment building read 800 rem an hour. So to give you a forget about LNT or anything else that you're talking about, if you walked into that containment for 30 minutes, you would have a 50% of chance of dying within 2 weeks. The amount of radiation that was released inside containment was extremely, extremely significant because we failed fuel. We melted all of that fuel, and we also had different paths for that failed fuel to travel into the containment atmosphere. We also did have, until they isolated these systems, we did have a path for the radiation to get outside of the containment building, but that was very, very minor. The actual ultimate amount of radiation that was maximally exposed to anyone off-site the plant that could have hypothetically been done is about 80 millirem, which is, just to give you an equivalent, that's 8% of what you would get if you just got a CT scan. And almost no one got that dose. And even the most conservative linear no threshold hypothesis models predict that less than one person would have died, whether it's in the operators or in the general public. So we have a situation in which the defense in depth philosophy that you see that characterize the Generation 2 and Generation 3 light water reactor build out ultimately works. So even in a system where we have a stuck valve, even in a situation where we have a stuck valve, an auxiliary feed water pump block valve situation break, even in a situation where the operator shut down the emergency core cooling system, we melt 60% of the core, we detonate hydrogen within the containment building, we get so much radiation that literally it's reading 800 rem inside the containment building. That system prevented any meaningful or any public health consequences to either the general public or to the operators of the plant, which in my mind is why one of the reasons why 3 Mile Island is one of the greatest sort of arguments you have for nuclear safety and for a real vindication of this sort of onion-like approach of defense in depth that nuclear engineers really pioneered starting in the late 50s when the nuclear industry began deploying nuclear power plants in the civilian realm. Now, what I want to say is the public response to this was really, really quite interesting.
I'm just curious, you mentioned the defense at depth philosophy in Gen 2 plants. Were there any civilian nuclear reactors built with no defense at depth, without an emergency core cooling system or an auxiliary feed water system? Or like what?
Oh, yeah.
What was...
So we forget that. So there's two examples. Yes, plenty. So there's a couple of examples, like Indian Point Unit Number 1, not Unit 2 and 3 that just recently got shut down by the idiotic anti-nuclear activists, but Unit Number 1, which was a small, kind of actually experimental 200 and some odd megawatt electrical plant, was actually shut down by the Atomic Energy Commission in 1974 because it did not have an adequate emergency core cooling system. And this is often, a lot of nuclear advocates talk about these changes that the AEC mandated, but actually it turns out that these sorts of safety changes in some cases were necessary, because had you not had these sort of emergency core cooling systems, for example, an accident like 3 Mile Island might not have been as easily terminated. But there's another example that people don't ever talk about, bizarrely, which is San Onofre Unit Number 1. Not Unit Number 2 and Unit Number 3, which were shut down in 2011, but Unit Number 1, which was one of the prototypical Westinghouse 3 loops. And this wasn't an emergency core cooling system issue. This was actually a radiation shielding issue. So remember how I talked about how that the containment building basically shielded the operators from this 800 rem an hour of death rays that essentially were emanating inside the control room, inside the containment, which would have harmed any operators or people who were around it if there wasn't that feet of concrete that was preventing that shine from getting out. In San Onofre, the original sort of containment building wasn't a classical shield building, but rather a sort of vapor suppression sphere. That was just a steel sphere that was designed to, take the pressure loads associated with a broken pipe. But it turned out when the AEC reanalyzed these issues in 1968, 69, and 70, they recognized that had we had exactly the sort of accident that we had at 3 Mile Island, where we had a massive sort of amount of source term that was outside of its normal place in the reactor coolant system, that the shine, that is the gamma rays that were emanating out of it, could actually pose a major threat to any operators that were nearby that sphere. So as a result, they mandated through the backfit rule something called the sphere enclosure building. So they literally built a massive 3-foot to 6-foot concrete shell around that sphere to basically prevent, in the event of an accident like TMI, where we had so much gamma shine, that the operators would still be able to, go into the auxiliary systems and get close to it without getting a deadly dose of shine. What's amazing about this is that AEC regulators and the industry itself, even before an accident like TMI, really recognize these, various sort of safety challenges that could occur and proactively responded to them even before an accident like this happened. And I think it's really important that, WASH 1400, the Rasmussen study, right, was before I go into the study, let me just make it a little more human. I think there was a little bit of a Titanic mentality in the industry at this time. If you think about where you are from a Babcock and Wilcox engineer, you say we have safety system after safety system, containment buildings, we have auxiliary feed water systems, we have triple redundancy in the auxiliary feed water system, we have two redundant systems in the high pressure safety injection system completely separated from each other. We have even a whole set of low pressure safety injection systems that can do a larger break. We have containment sprays. We have the ability to cool the reactor through natural circulation. There was this idea that there was so many safety systems that they really never accepted the idea, to some extent, that there really could be serious core damage and a serious meltdown scenario. And if you talk to people in the industry who are going through this, it wasn't until 1983 and 1984 when they actually opened up the TMI reactor pressure vessel and actually put a camera down through a borescope and look through the core. And there's actually videotapes of people watching them lower this camera down, and you hear the gasps as they're going below the point of the core top plate and they see nothing. And they recognized that they had melted a huge amount of the core. There's a almost Titanic-like mentality that this couldn't actually really happen, but it did. And I think it says, on one hand, an immense credit to the engineering acumen of the nuclear engineers of this generation, that they had been proactively working to anticipate safety challenges and build systems that were deeply redundant, even for human error. And I think that's an immense credit to the industry. But I want to flip back and say, I think there's a sort of an end maybe on this note. There's a little bit of that mentality that's coming back, I think, right now in the US or around the world, where I think some people argue, the safety impacts of a LWR meltdown, can never really be significant to the public. And I don't think that's true. I think that I think the analogy with air travel is great. No one would argue that, when you're traveling at 35,000 feet in the air at 550 miles per hour, that's not a dangerous sort of intrinsically activity. Of course it is. But we have systems that make it safer than driving on the road, right? And the same thing I think applies to nuclear, right? This is an activity that has the potential to have safety threats and challenges to public health, but we have engineered marvelous systems both on the human training side, which we'll get to the next episode, the engineered safety features, and a culture of safety that has made this the safest form of generation, even such that at 3 Mile Island you didn't harm a single person or injure a single person.
Interesting. And we're now moving into, or we have moved into a generation of reactors where a lot of those systems have been simplified and made passive to save money, not necessarily make them more safe, as you've said.
Just to give you an example, on the AP1000, the pressurizer is now large enough that there are no pilot operated relief valves at all. Right, that even in a serious feed water transient, the system is able to have enough volume in the pressurizer such that you don't need PROVs at all. So we've just completely eliminated this sort of accident sequence from occurring.
Cool. Any other details like that? Because I think that's really neat.
There's plenty.
Okay.
Sure. There's hundreds.
Okay.
We should really talk about what the response was.
Sure.
So, the development of SPUDs, right, of safety parameter display systems to prevent this exact sort of operator disorientation, to have a single screen, even in 1981, that would display on one screen every single safety critical parameter simultaneously so the operators could look at it. But we'll get into that in the next episode. I think that's really good.
Okay, James, thanks again for coming on. Bye for now.